Hi everyone. So we are continuing our videos about house and its applications. And on this video, we're going to discuss the results of our recent publication on a very interesting topic, which is the construction of discrete time systems, so chaotic maps that showcase an absence of fixed points, so they have hidden attractors, and at the same time they achieve robust chaos. So, the results are from this paper, which is called the family of 1D modulo-based maps without equilibria and robust chaos, and an application to a PRBG, a pseudo-random bit generator. So I'm going to explain everything in this topic. The paper is published in an amazing and excellent journal, which is the Nonlinear Dynamics. Very good quality work. I'm really excited about it. So, basically, the topic of this paper has to do with chaotification. Okay, I have a previous video also discussing this topic. The idea behind chaotification is this. Just because there are far too many maps at the moment in the literature, basically for me as a researcher, there is really not much point in designing just one new chaotic map because there are already many maps existing. So the idea is that instead of designing new maps again and again and again, we basically find a new technique which we can use in composition with any of the previous existing chaotic maps in order to design not just one map, but a family of maps, possibly with desirable properties. Okay, so when I say there are a lot of maps in the literature, I mean, even if you are not extremely familiar with chaotic systems, you may already know a couple of maps, like the logistic map, the tent map, the sign map, the Renui map, the Chebyshev map, and these are just 4 or 5 of the basic maps. In the literature, there are hundreds of maps, okay? So the idea is that I want to design a new function, f capital, which when composed with f small, which is the original map, is going to give me a new family of maps. And these maps should generally have richer chaotic behavior. So what do I say by richer? What do we mean? Richer behavior can mean a collection of different topics depending on what are my goals. Okay, so one very good goal is that with this new chaotification technique, I will always achieve robust chaos. Okay, super important property, and of course, both theoretically interesting, but also of practical interest. Robust chaos means that for a specific range of parameters, I don't have periodic behavior at all. I only have chaotic behavior through and through for a collection of parameter values. Okay, so this is very desirable in applications like encryption. Okay, but apart from that, I may want to have other types of goals in mind. So one goal is to have hidden attractors. Hidden attractors appear where you don't when you don't have a fixed point, when you don't have equilibrium in the system. I may want to achieve coexisting attractors which may not be present in the original system, and let's say I want to have them. I may want to achieve offset boosting, which is the idea that I can actually move the position of the attractor in the phase space. I may want to achieve tunable statistical properties, another very desirable property. I discuss about it in a different video. Okay, so I may have different goals in mind that I want to achieve using chaotification, and this is why I say that the process and the goal of chaotification is to design new maps that have richer behavior. Whatever you have in mind with a goal when achieving more rich behavior, okay? But basically what we usually want to achieve is a higher key space, so more parameters, robust chaos, which is extremely important. I think most of the time there are many papers in the literature, but most of them aim at robust chaos, okay, which is very important property. But you may want to achieve any other goal, okay? So, we have a very interesting codification technique. Let me move my camera a bit. We use basically the modulo map. The modulo function creates discontinuities, and discontinuities are very useful for us because they increase security and also they help us basically control the domain of the function. Okay, so what we do is this. We have a seed function f that you see right here. This is the original map that we are using, logistic tent or whatever other map. So the original map function, the seed map, if you like, we scale it by multiplying it by a parameter beta. We add a stable parameter alpha, and we also add the value of the map xi minus 1. Now, this looks a bit random. It is actually not random at all. There is a geometric interpretation behind this design. So basically, we design this function by geometrically interpreting what we want to achieve. Okay, and from this function, we also pass it through a modulo in order to scale it down and control its mapping domain. So the geometric interpretation behind this is that we design the chaotification technique in such a way that we manage to achieve to avoid any intersection with a bisector in the phase space. So in the phase diagram, when we achieve that, basically you don't have any equilibrium in the map. So we have two very important theoretical results for this family of functions. I have them right here. The first one is that under specific parameter values a and b, we manage to achieve a complete absence of equilibria. As I said, the function in the phase diagram doesn't have any intersection with a bisector, so the map doesn't have any equilibria. So if an attractor exists, it is a hidden attractor because there is no intersection with any basin of attraction of an equilibrium. This happens, of course, because we don't have any equilibria at all. And the second theoretical result, which is very, very important, is that we show that under specific parameter values, we manage to achieve a higher Lyapunov exponent compared to the seed function. Okay, so basically at the same time, for a specific range of parameters, we can manage to achieve robust chaos and hidden attractors. So this is, I think, the very first work that addresses this topic for discrete time systems. Okay, and after we saw these theoretical results, we have a collection of different chaotic maps that we tried. We consider three different seed functions. So one of the first functions we consider is the sinusoidal function, as you see right here. This is inspired, of course, by the sine map, which is a very well-known chaotic map. So on the left, you see one example of a phase diagram, and indeed, you see that the phase diagram doesn't intersect the bisector. So this is an example of a map that has hidden attractors. Okay, this doesn't appear for all parameter values, but we actually show in the paper, which I put a link in the description at the end, where you can see the specific parameter values under which this map manages to achieve hidden attractors. And on the right, you see a graph of the Lyapunov exponent values for a very big range of parameters A and B. Now, in this example, we don't achieve robustness because you see that there are, in many regions, dense transitions in and out of chaos, which are of course symmetric. You see right here, probably due to the fact that the sign is periodic. So we have symmetry as the parameter alpha increases. And we also have this sort of fractal structure. So we have a self-similarity and a dense transition in and out of chaos. Okay, so this example has a very interesting shape in the Lyapunov exponent diagram, but doesn't show robustness because we go in and out of chaos all the time. But for different parameters, as you see right here, for example, in the tanh, we managed to achieve robust chaos. Okay, you see here in the diagram, there are no black values. Black values indicate periodicity. So for a very big range of parameters, the Lyapunov exponent is actually always positive. So we managed to achieve robust chaos here. Okay, and for a subset of these parameter values that I have inside the paper, we also managed to achieve an absence of equilibria. Here I have just an example of a phase diagram where you see that the diagram of the function doesn't intersect, the bisector. So we actually have hidden attractors here and robust chaos for a specific subset of parameter values. And we also considered a third example, which is inspired by the RenV map, a very well-known map. This map uses the modulo function, so this is why the phase diagram has a lot of gaps, a lot of discontinuities. Again, we managed to achieve absence of equilibria and robust chaos at the same time. So we consider three examples, and 2 out of 3 actually have robust chaos. So this is very, very important because, as I told you, robust chaos is very useful for applications. Now, for that matter, we also considered a specific, very interesting pseudo-random bit generator. Now, we have designed a generator which is specifically catered for chaotification techniques. And I say that because this function, this PRBG, uses both the value of the map xi, but also the value of the seed function that we use in chaotification. So it has f of xi minus 1. Okay. And we use the remainder operation for hashing, but also exclusive OR, in order to have an intertwining of the bits before we proceed to having the output bit stream. Okay. This bit stream has a bit more operations, but it has an overall very good operations per bit ratio. It outputs in each iteration 64 bits, so we have a lot of bits per iteration, and the ratio of operations per bit is 10125. Okay, so it's a very good ratio, and I would dare say with appropriate designing, it actually can manage to achieve a very, very good speed. And also it has a very, very high security because it interplexes in a very clever way the intermediate bits before producing the output. Of course, we tested all of the NIST statistical tests, and our maps passed the NIST test successfully. So it is useful and can be used in practice, like in any application related to encryption. Okay, so this is a very good example that the maps that we have generated are actually applicable in practice. Okay, now, as I told you, I consider this work to be very, very useful, very interesting, and for that matter, there are a lot of future topics that we can consider. Now, as I told you, the point behind chaotification is that you can use any seed function that you like. So in the paper, we tested three different functions: sinusoidal, tan, hyperbolic tangent, and modulo from the Renui map. Okay, but actually, you can study many, many more families of maps using any seed function that you like. So the tent map, the logistic map, the Chebyshev map are all possible applications for this specific chaotification technique. Okay. So you can read the paper. I will put a link into the description, and you can actually study and consider many maps of your own. Second very interesting topic is the fact that in our paper we have generated hidden attractors, so there is no period one behavior. We have completely eliminated the existence of fixed points, so period one behavior doesn't exist. Still, it is possible to have period n behavior, period 2, period 3, period 4. So a much bigger problem mathematically is to design a chaotification technique that can completely destroy period n behavior. This is very challenging mathematically, and it is still an open problem and a very, very interesting problem. Okay. Now, the geometric idea behind our function was to utilize the modulo function to achieve this sort of chaotification without equilibria. Another open problem is whether we can achieve this sort of chaotification without equilibria using trigonometric functions. Another interesting problem in designing mathematically uh, chaotification techniques, which is an open problem, of course. And also, as a final interesting topic, if you are interested in fractional calculus, you can actually design a fractional version of this codification technique. Fractional chaotic systems are very, very rich field in the literature. It's not my direct research interest, but I believe if you are interested in fractional techniques, designing a fractional version of this codification, it's a very, very interesting topic. So as you can understand, you can take this work and consider many, many, many problems for future studies. All of them, from my perspective, are extremely interesting. Okay, so I'm gonna have another series of couple more papers discussing different chaotic maps without equilibria. So I'll see you in the videos that will come next.